Okay, we are going to look at another superposition problem of electric forces. This time they are in a grid-like format. So we have four charged particles. Q1 is 4 microcoulombs. Q2 is negative 3 microcoulombs and is 2 centimeters to the right of Q1. Q3 is negative 3 microcoulombs and is 2 centimeters above Q1. And Q4, we don't know, but it's located up and to the right of Q1. So the question is, what does Q4 have to be in order for Q1 to remain stationary if it were allowed to move? So imagine Q2, 3, and 4 are all fixed to a board. I plop Q1 in there, and I want to know what should Q4 be for if I plop Q1 in there, it doesn't move. So what does doesn't move mean? Well, it means it experiences no net force. So the crux of this question is, what is Q4 if Q1 has a net force equal to 0? All right, that's the crux of our question. Okay, well, we want to think then about what is the net force on Q1. And we know that the net force on Q1 is equal to the force on 1 by 2 plus the force on 1 by 3 plus the force on 1 by 4. The vector sum, of course, of these three forces. So let's start with each one of those interactions and then look at the vector situation that we have. So let's start with the interaction of force 1 by object 2. These are electrical forces, so this is our K, Q1, Q2, all over the radius between 1 and 2, quantity squared. So that's 8.99 times 10 to the 9th. Q1 is 4 times 10 to the negative 6th. And Q2 is negative 3 times 10 to the negative 6th, all over the radius between 1 and 2, which is 2 centimeters squared. So what is my force on 1 by 2? 269.7 newtons. Now, it's negative, which tells us what? It's attractive. So if I look at this image, Q1 is feeling an attractive force to Q2. Attractive for Q1 means it's to the right. So this is 269.7 newtons to the right. All right. How about between Q1 and Q3? Well, that's K, Q1, Q3 over the radius between 1 and 3 squared. So again, our K is 8.99 times 10 to the 9th. Q1 is 4 times 10 to the minus 6th. Q3, also minus 3 times 10 to the minus 6th, all over the distance between Q1 and Q3, which is also 0.02 quantity squared. Well, those are the same values, and we find that the force of 1 and 3 is also minus 269.79 newtons. The negative electric force tells us it's attractive. And therefore, if I consider what does attractive mean in this situation, Q1 is feeling a force upward by Q3. Well, what about Q4? The force of 1 and 4. Well, that's K, Q1, Q4, between the radius of 1 and 4 squared. Right? Well, it's the same process. 8.99 times 10 to the 9th is our K. Q1 is 4 times 10 to the minus 6th. I don't know Q4. But I do know the radius. If this is 2 centimeters and this is 2 centimeters, I can find the radius. Our radius is, if we think about that Pythagorean theorem, it's 0.02 times the square root of 2, quantity squared. All right. I don't know Q4, so I'm stuck at this point for finding the net force on Q4 right now, by Q4. So how can I do that? Well, I want to recognize this sum equal to 0. We can do a force analysis on these objects to determine what that force 4 might look like. So let's draw a free body diagram of Q1. There's my Q1. I know I have a force to the right of 269.7 newtons. I also know I have a force acting upward of 269.7 newtons. But I don't know what my force 4 is going to be. Now, I could start making some intuitions about it. We're going to find out how to find it, but I could start making some intuitions about it. If I have a force to the right and a force up acting on the object that I want to ultimately be 0, then I need to have a force that's going to be down and to the left. My force 4, I can predict, is going to be in this direction. We're going to find that out, but that's going to be my prediction. So we know there are 3 forces acting on the object. And those forces can have both horizontal and vertical components. So we'll say our force to the right is force 1, our force to the up is force 2, and force 4 is going to be number 3. So force 1 is only horizontal. It's positive 269.7. There are no vertical components. Force 2 is only vertical. It's positive 269.7. There's no horizontal components. Force 4 could have a horizontal component and a vertical component. So we know the force on 1 by 4 has a horizontal component, and the force on 1 by 4 has a vertical component. And those are the 2 components of the force 1 by 4 and the force on 1 by 4. So now we can sum those forces. So we have 269.7 plus the force on 1 by 4 horizontal. And we have 269.7 plus the force on 1 by 4 vertical. Because we said Q1 doesn't want to move, we know that the sum of these forces, both in the horizontal direction and the sum of the forces in the vertical direction, must equal 0. So I bring that down. We find that our horizontal component is equal to negative 269.7 newtons, and our vertical component is negative 269.7 newtons. Now you might have been able to deduce that since these 2 were the same, but it's valuable to go through the process in case they were slightly different. All right, well now I have my 2 components of my force 4, so I can find the magnitude of force 4. So the magnitude of this force on 1 by 4 is equal to the square root of negative 269.7 squared. Plus negative 269.7 squared. And that gives me a magnitude of 381.4 newtons. And I can find the angle of the force because the angle is the inverse tangent of negative 269.7 over negative 269.7. And that's going to give me 45 degrees in my calculator. But when I have two negative components, let me just put a break here so we can kind of visually see this a little better. When I have two negative components, my calculator is telling me it's a positive 45, but I have to add that 180 degrees to that 145. So 180 plus 45. My true angle is 225 degrees. So force 4 is acting at 225 degrees. All right. Still don't answer the question yet. We want to know what is the charge on object 4. So, kind of running around a little bit room here, but force 4 right here is where we ended and went to this analysis. This gives me the magnitude of the force. So if I define this as just the magnitude, we know that this force 4 goes into this equal. So I'm going to erase this. So I have my little room here. And we see that this is 381.4. So force 4 is the magnitude of our electric force. Now, let's erase this. If we know that force 4 is the magnitude of the electric force, and we know it is acting at an angle of 225 degrees. So we can solve for our Q, our charge, on object 4 using this equation. One of these days I'll have a quicker method of erasing this board. These long problems that we get. Okay, so I'm just going to rewrite this in this area. We have force number 4 on 1 by 4 is equal to 8.99 times 10 to the 9th. Q1, which is 4 times 10 to the minus 6th, times Q4, which I do not know, all divided by 0.008, I think is our, if I calculate this out. And that equals 381.4. All right, so I just rewrote this up here. This lets me solve for Q4. And when I do the algebra and solve for Q4, I get Q4 has a value of 8.48 times 10 to the negative 6 coulombs. So 8.48 microcoulombs. And since we're just dealing with single digits, this will be 8 microcoulombs. So it has a charge value of 8 microcoulombs. But we're not quite done yet because I still need to figure out the direction. So this equation gave me the magnitude of the force. Let's be explicit about those magnitude bars again. How do I know the direction of the force? The direction of the charge. Is it positively charged or negatively charged? Well, remember we said that the angle of the force on 1 by 4 was equal to 225 degrees. That's down and to the left. That means if the only thing in the world was Q1 and Q4, the force Q1 would feel would be down and to the left. Relative to Q4, down and to the left is a repulsion. So this angle of force on 1 by 4 tells us that this is a repulsion. But remember, I have to look at my picture. If it's a repulsion, that tells me Q4 and Q1 are of the same sign. So this implies that Q1 and Q4 are the same sign. All right? Well, Q1 is positive. So Q4 has to be a positive value. And we get a positive value for our charge on Q4. So if I were to place an 8 microcoulomb charge at that spot, then dropped Q1 in there, and it wouldn't move. The net force on Q1 would be 0. All right, so using Coulomb's law and going back to some of that force analysis where we break things up, recognize that the net force is equal to 0, solving for the components of the force that we want, determining the angle of the force that we want, telling us that that means something about that electrical interaction, and we can solve for both the charge of the particle as well as whether or not it's positive or negative. All right, lots of space. Good job.